I welcome you to our Crew Plus Academy webinar. My name is Chris Corbin. I'm the Program Manager for Marine Pollution and Communications with the UNEP Cartagena Convention Secretariat. We are one of the regional co-executing agencies for the project, along with our colleagues from the GIZ and the Organization of American States. Before we begin, please note that the session will be recorded and uploaded to our Academy website. And if you do not wish to be recorded as part of or be part of the recording, I kindly request that you leave the session now. Today's training is session 5 of our Block 2 Crew Plus Academy, and the focus will be on case studies, implementation of medium-scale reuse systems. The training is offered through the Crew Plus Academy, a free platform that brings together in one place all the training initiatives led by the Crew Plus project. And we are wanting to create a space for knowledge sharing of effective and practical water and sanitation solutions in the wider Caribbean region. As we've done in previous weeks, we are asking you to participate in 2 surveys, 2 online surveys. The first one is to be done now and is a roll call, which you can see on the screen and in the chat, and will be used for formal registration purposes. The second survey is an evaluation survey, which will be done closer to the end of the session. This end of session survey will also be used to register your full participation today and will be the basis for the provision of your certificate of participation. We now just allow a couple of minutes before we start for you to complete the registration and the online survey, and we'll be back again in the next 2 or 3 minutes. Thank you so much. Okay, I just see someone mentioning that the link wasn't working, so perhaps we could just double check that. If anyone else has had any challenges, please let us know in the chat. But we will definitely, if there's a problem, try to rectify that or work with individuals who might be having specific challenges. Some said it's working for them, others not. So what we might do is during the course of the session, just try to work with those that it's not working with, so that it seems to be someone, a few people are suggesting that they had to copy and paste it in the browser. That might work as a solution. If that still doesn't work, then we'll we'll make sure to make a note of the persons who have who are here, as that's important for the record of the training. So we apologize for that slight technical glitch. That's the challenge of doing everything online. But I think in the interest of time and this particular session, for those who are still having challenges, if you could just try and work through them while the session is going on, we would really appreciate that. So thank you again. I think we're ready to go. Let me very quickly just introduce again our program facilitator and training expert, Gustavo. Gustavo, a specialist in water and sanitation, a background in engineering, and as we've seen over the last 5 sessions, very, very knowledgeable on in the field, but also in communicating things in a very simple and practical way. Over 25 years of experience in supporting basic services in developing cities in several regions. So without any further ado, Gustavo, welcome again, and the floor is yours.
Thank you, Chris. Good morning to everyone. Happy to be here. This is our session number 5 from 6 sessions. For today, I have prepared a selection of interesting international cases, international experiences on wastewater treatment and reuse. As you can see on the screen, these are experiences from different countries, very distinct cases that will complement each other. We will go from larger, more centralized cases, as Aquapolo in Brazil, number 1, to more decentralized, smaller, more distributed cases in the other countries. So the idea is to show that we need different solutions for different locations, for different needs, and for different purposes. So I think that this selection of cases complement each other in a way. So let's start with Brazil, the Aquapolo experience. Aquapolo is the name of a company that has been created in Sao Paulo, in Brazil, in the year 2012. The challenge they faced was to generate some treated wastewater for industrial reuse. You can see a picture of the facility, very high-end facility that is capable of actually retreating wastewater in order to achieve a degree of treatment suitable for industrial reuse. As I mentioned, this Aquapolo company is called Aquapolo Environmental. Company was created for a specific purpose, and the stakeholders of this company are the main utility in Sao Paulo, Sabesp, and also this other company called Inima Brazil. So they have invested in designing and implementing this treatment plant. This new company signs a contract with Brasskim, Brazil. Brasskim is a very large petrochemical company in Brazil, which is located, some of their plants are located in a petrochemical pole in Brazil, very important operation there. And so they signed a contract with this newly created company for 43 years. And they assure they will buy a treated effluent of at least 300 liters per second, and they will use that effluent for 43 years and an extendable period of 10 additional years. The total investment for this plant was $23 million. 25% of this investment was paid by the shareholders, and 75% was financed by the Brazilian Development Bank. Even though the minimum demand for reuse was guaranteed to be 300 liters per second, the expectation was higher, and the treatment plant was designed for a capacity of 1,000 liters per second. So a very large plant. Here's a close-up of the plant. You can see urban centers, cities in the background. And here we can take a look at the treatment train for this plant. So, so there are several municipal wastewater treatment plants in Sao Paulo. One of the larger ones is called ABC Wastewater Treatment Plant. So after the water goes through the conventional ABC treatment plant, then it comes into the Aquapolo operation to receive basically tertiary treatment. The first tertiary treatment it receives is done through biodiscs. Biodiscs are discs that spin. Half of the disc is within the water, half of the disc is outside of the water. So as it spins, it gets wet and dries up, wet and dries up. So it's an aerobic system used mostly for nitrification and denitrification processes. So basically to remove nitrogen from water. Very interesting technology, very compact. Biofilm develops on top of the discs, and this biofilm is exposed to water and to the air on and off. So that's why this is an aerobic process. And then we go to an anoxic reactor, very little oxygen there, to complete the denitrification process. After that, the treatment train divides in two parallel lines, one with ultrafiltration and the other one with reverse osmosis. So this ultrafiltration process is a finer, much finer filter in order to reach a higher level of treatment suitable for the industrial purposes they needed to serve. And the reverse osmosis process is meant for demineralization of the water in this case, also for industrial processes, probably for a different client. So we have two different pipes taking the treated effluent 17 kilometers away from the treatment plant and towards the industrial area in which the clients are located. So this is where the impact and the benefits of this operation that started in 2012. Currently, the demand is 650 liters per second. Remember, we have a capacity of 1,000 and a guaranteed minimum demand of 300. So currently is twice as much, is generating twice as much as water as they started with. And the main benefit is that this is reducing the need of exploiting drinking water. So before this plant was built, all these industrial companies would take water from the drinking water network. So what they have done is to replace this the drinking water network as a source for this reclaimed water. And if you can see in the background, in the back of the picture, there's a purple pipe. That purple color denotes that is treated effluent for industrial reuse. We usually use that purple color for that. And the companies that use this water end up with savings of about 33% as compared as the tariff they used to pay for potable drinking water in the past. So there's a big savings for the company, for the companies, for the users, final users. But on the utility side, there's big savings on the production of drinking water, so that drinking water can go to other users instead of going to industrial purposes. So that's the main benefit. Also, the companies, the industrial companies, stop relying on water from the river because the river changes its quality over time also. Some of those companies would take water from the river and treat that water themselves and then use it. But since the river would change its conditions during the rainy seasons or sometimes it would become turbid, then the quality of water was very variable, and these industrial companies had to deal with that. So now they have a more stable supply, which is less dependent on weather conditions. So that's the final results that they have obtained in several years of working with this plant. I will share the presentation in the resource section of the Academy website, and you will have access to all these links in which you can get much more information, more details on all the cases I will present. Let's move on to Chile. This is the Mapocho project in Chile. A very interesting project. It took place several years ago. The problem they had was that wastewater was not being treated in the metropolitan area of Santiago, and they were polluting rivers, and people were using the water from the rivers for agricultural irrigation. And in 1991, there was a cholera outbreak, and new laws were passed in Chile that prohibited the use of polluted water for irrigation in order to protect the health of the citizens. So that's after 1991 is when they start developing these new restrictions of water reuse, and the government starts a very large wastewater treatment program for the greater metropolitan Santiago area. And this program was implemented between 2001 and 2012. And these very large plants were implemented, at least 3 of them, El Trebal, La Farfana, and Mapocho. The last one is the one we're looking at in this case, Mapocho, which was built in 2012, as well as the previous case. The owner of this treatment plant is the utility operator of Santiago, Aguas Andinas. This is a subsidiary of Suez Group. The plant has a capacity of 380,000 cubic meters per day. The initial investment was $150 million US. And what is very interesting about the Chilean case is that Chile has a very advanced subsidy system. All households in Chile are categorized depending on their income level. So they have this huge national database of households and their income level, and the subsidy is directed specifically to households that belong to the lowest income levels of these categories. So instead of subsidizing to a specific municipality or a certain area of the city, the subsidy is direct to people who need the subsidy. So this, the result of this system is that the people that have the lowest income pay a much lower tariff than the rest, based on their income, and that's how they have managed that everybody has access to drinking water, also to wastewater treatment, because everybody is paying a tariff that they can that is affordable for them. If we take a look at the treatment train for this system, we will see that it's very complex, because the challenge here was to treat the wastewater to a level that will not pollute the rivers at all, since these rivers are being used for crop irrigation. So the reuse in this case is indirect reuse. So instead of directly irrigating after the treatment plant, the water will go into the river, and the river becomes source water, either for drinking water and also for crop irrigation. In this case, we have a pre-treatment phase in which we have a grid chamber for all the sand that might come along with the wastewater, automatic screens, and a compacting system. Since we have a large plant here, there's a lot of solid waste coming with the sewer, and this part of equipment compacts all this solid waste so it will take a less volume to be taken to the solid waste management system in Santiago. Then we have the primary treatment based on a primary settler. After that, we go to a secondary treatment based on activated sludge. Activated sludge, as you know, injects air bubbles into the mix of wastewater and aerates the whole activated sludge tank. So in order to ensure this aeration, we use blowers. Blowers use energy, so this is a very energy intensive process, but also very efficient from the perspective of reaching a high quality effluent. So it removes a lot of organic load, BOD, in this process. Then we have a tertiary treatment on a secondary settler, in which we're clarifying the water. And finally, the discharge into the Mapocho River, as I mentioned, for indirect reuse. Something we have to take into account is that every single treatment plant always generates these byproducts and other treatment lines. It's not only the water. At the beginning of the plant, in the pre-treatment phase, we're separating grit, we're separating in other plants, we're separating fat, we're separating sand, we're separating all the solid waste, right? All that has to go to specific disposal. And also, every single plant will generate all sludge, because we're separating the solids from the liquids. So if we have a very good plant, we will have very pure water on one side, and we will have a lot of sludge on another side. Now, this sludge can also be reused to improve soil, for example, for agricultural purposes. It can also be burned to be used as energy for making cement or bricks or briquettes. So there's different uses that we can think of also for sludge. But the sludge is part of the problem, and it's also an opportunity for reuse. In this case, the sludge line goes through a hydrolyzation process. This is a process that elevates the temperature of the sludge to very high temperatures, up to 140 to 165 centigrade. And then it goes down to atmospheric pressure, and these changes of temperature and pressure basically sanitizes the sludge. It disinfects the sludge. So if we have E. coli, or we have still viruses or bacteria or helminth eggs, all that would be destroyed through this process. And it also will reduce the volume, the total volume of sludge, in about 20% before we go to the stabilization process, which takes place in an anaerobic reactor. And when the sludge goes through the anaerobic reactor, it generates a lot of biogas, which is a mix of basically methane and CO2. This biogas can be burnt, and when we burn it, we can generate also electric power. In this case, we're burning the biogas out of the anaerobic reactor. That heat helps the hydrolyzation process, so we are reusing the heat generated for the hydrolyzation process, and also part of that is turned into electricity, and that electricity is used for the blowers in the activated sludge phase. Now, maybe it doesn't cover all the energy requirement for the activated sludge phase, but it will reduce the consumption of electricity. So, so the company can get savings.
¿De qué? ¿De celular?
Some of the impacts and benefits that were generated in this system in Santiago, basically the health risks of the river water were virtually eliminated. no more cholera outbreaks happen afterwards, and the quality of the rivers is very, very good right now. The area under irrigation with safe water reaches around 130,000 hectares, so very significant irrigation area. And on the other side, this type of solution requires high investment cost, and it has also a very large carbon footprint of the treatment process because of the use of energy. And here we have also some references that you can access to afterwards at the end of the presentation. Now we will move to Nicaragua, to Lake Managua. Lake Managua is the largest water source and water body in the region. The city of Managua is basically next to the lake. This project dates from 2009. The challenge was to protect Lake Managua. The local name of the lake is Solotan. The challenge was to protect this lake from domestic and industrial wastewater pollution. A large protection and rehabilitation program was established back then. The objective was to treat all municipal wastewaters, and the treatment capacity of this plant is almost 300,000 cubic meters per day. So this is also a large plant. It can serve up to 1.1 million people, but it's different from the previous one because the technology is much simpler, and we will look into that. From the beginning of this project, there was a reuse intended for water, indirect reuse because the water is discharged into Lake Managua, and there's a lot of fishing going on there, also recreation. So the idea of protecting the lake is to be able to reuse the water of the lake as before. But there was also an additional reuse in agriculture for the sludge generated in the plant. The owner and operator of the plant is the ENACAL, that's the Nicaraguan utility who operates in Managua. And the financing for this project came from the KfW, the German Development Bank. The total investment cost was 25 million euros. Here you can appreciate the plant. These round structures in the center of the plant are trickling filters. We will look into this in more detail. And these greenhouse looking like structures in the back are the facilities for drying and processing the sludge, which also we will look into more detail. Now I will share a short video on this case that is very interesting. And after that, we can have some questions also on the cases we have gone through.
Fishing on Lake Managua. For many locals, it's still their only source of income.
So now it's no problem for us and our families to eat our catch.
The wastewater treatment plant is located on the outskirts of Managua, the Nicaraguan capital. For decades, the sewage from more than 1 million people flowed directly into the lake. But that all changed in 2009. Now, 2/3 of Managuans are connected to the sewer system, and their sewage ends up here. During a tour through the treatment plant, students learn about water management. The plant's operator explains that more than 90% of the solid matter is filtered out. That still doesn't make the water safe to drink, but it's much cleaner than before. Using the latest technology to produce clean water, many of the students see this as a dream job.
The sewage treatment plant in Managua is the first of its kind in the region. There's nothing like it in all of Central America.
The project cost some 25 million euros. Funding was organized by German development bank KfW and provided by the German Ministry for Economic Cooperation and Development. In 2 years' time,
Well, I thought you were coming with news.
and her team from the Nicaraguan water supplier, Inacar. By that time, the local technicians have to be fully trained to run the plant without help from abroad. A new idea is to cut down on operating costs. The sewage sludge is aerated and left to dry in the heat until it forms a granulate, producing a new, all-natural fertilizer.
The first farmers are coming and picking up this granulate at their own expense and experimenting with it.
The first customer is a dairy farmer, though no ordinary one. Ricardo Coronel Kautz used to work for the Ministry of Agriculture. Now he uses the granulate from the sewage treatment plant to fertilize the grass in his pasture. Does he think it's a good alternative to chemical fertilizers?
I think it can soon replace synthetic fertilizers. The world's population is increasing, so it's a step in the right direction. In China, it's common to use human excrement, and we need to start doing that too.
Switching to the new granulate could save a farmer around 30 tons of chemical fertilizer a year. That's cost-effective for the farmer and for the sewage treatment plant, since it no longer has to dispose of the sludge. It's good for the environment as well. Synthetic fertilizers are usually made from fossil fuels.
The more people use waste products to replace synthetic fertilizers, the more they contribute to the reduction of CO2 emissions.
Reducing greenhouse gases and improving water quality have proved a boon to the ecosystem of an entire region. Lake Managua is connected to the much larger Lake Nicaragua, which lies some 50 kilometers southeast of the capital. On the western shores of Lake Nicaragua, we find the city of Granada. Its lovely colonial-era buildings have made it the country's biggest tourist destination. But just a few hundred meters away from the city center, the view is less appealing. Barely a quarter of the households here are connected to the sewer system. Helge Jan from the KfW has an appointment with a man from the public water utility. The development bank is willing to offer funds to treat the sewage, which is already contaminating the city's drinking water. If nothing's done, people could become ill.
The sanitation problems are reflected in the health of the people. There are many infectious diseases. The wastewater problem doesn't just look unsightly, it also affects people's health.
Helge Jan wants to help.
The number of residents in Granada connected to the sewer system should rise from 20 or 25% today to 80%. The second part of the project will be to overhaul the existing sewage treatment plant that's not working properly.
Even after it's been treated, the water still looks like this. contaminated with algae and residue from detergents. More than 17 million euros are to be invested in Grenada to improve water quality and keep the lake clean. That's vital. Lake Nicaragua is the largest drinking water reservoir in Central America.
Right, so that was the case of Lake Managua, Nicaragua. Now let's stop this. Let's look at the treatment train here for this plan. Get my camera back. Okay, as usual, we have a pre-treatment stage. In this case, we have screens, then we have a grit chamber and fat separation. After that, for primary treatment, we have a lamella settler. I don't believe we have seen specific lamella settlers in our session 2 on technical issues, but a lamella settler is a very efficient settler. We can settle solids just in a tank, right? As long as you give water enough time sitting in one place, you will end up settling all the settleable solids in the bottom. But when we have a large flow, then we need larger and larger tanks for settling. So this lamella settler is basically a tank with inclined plates inside the tank. So these plates break the movement of the sediment in the water. So as water is trying to go up, then it stops the vertical speed of the particles and make them settle in the bottom. So that's what the lamella settler is. So whenever you see several plates, inclined planes, then this is a lamella settler. Then the trickling filter, those were those cylindric tanks, very large tanks. These are actually empty tanks. They're not filled with water. They are filled usually with some type of media. It can be gravel, or it can also be plastic pieces, and we trickle water on top of these pieces. There's an arm that turns around, as you have seen in the video, and trickles the water all the way down through the plastic pieces, and you collect the water in the bottom. So in each gravel piece or in each plastic piece, a biofilm is developed. And when this biofilm gets in contact with the trickling water, then the microorganisms in the biofilm take up the organic, some of the organic load and from the water, and that's how this filter works. Then we have a secondary settler, also using lamellas, and finally the discharge, that is the discharging the treated effluent into Lake Managua. In this case, they are pumping the water to Lake Managua. In parallel, as always, we have the sludge line. The sludge goes through a stabilization process in an anaerobic reactor. Then it gets dried using a solar drying system. And this is what makes this plant very interesting. And after that, the sludge, the dried sludge, is ready for reuse. In this case, the sludge is being used for soil improvement, so for agricultural purposes. This is the drying, the solar drying system. It's basically like a greenhouse. It's over 1,000 square meters, so pretty large, 116 meters on one side and 11 meters on the other side. This equipment you see in the center of the picture is a mechanized equipment to turn the sludge. So in order to ensure the sludge is being dried, this equipment is constantly turning the sludge. When we have a smaller, more decentralized plants, we can turn the sludge manually with shovels or with a small tractor. No, this is a little bit more sophisticated in order to automatize the process. Also, near the roof, we can see fans in order to force some air out and get humidity out of the greenhouse and make the system more efficient. Nevertheless, this system is low cost, energy-wise is very low energy consumption. In this case, they are using 20 kilowatt hours versus 800 or 1,000 kilowatt hour that they would otherwise use using industrial dryers such as a centrifugal system, for example. The time it takes to dry the sludge in these facilities around 30 days, and the final product is about 87% dry matter. So that's very dry. It's very good for moving this sludge to other places where it's needed for reuse. As we mentioned before, the total investment was around 25 million euro for this plant. From those 25 million euros, about 5 million euros were invested in this drying facility specifically for sludge. This is one of the largest facilities for drying sludge this way, using this specific technology, which I find is very appropriate for the area and for warm places. Lets you do a very good job at drying the sludge at very low cost and very low energy consumption. Some impact and challenges of this project: the concentrations of BOD in the lake were reduced as compared as the levels before the plant was implemented. The water is much clearer now. But on the other hand, the oxygen levels have not really improved in the lake. And even though the municipal wastewater is being treated in this facility, there are other effluents that are still going into the lake that are not being treated, coming mostly from industrial activities and also runoff from agricultural fertilizers. So there's still some nitrification going on in the lake due specifically to other industrial effluents and also the excess water from irrigation that still contains fertilizer residues, nitrogen, phosphorus, and that's still a challenge that the lake is facing. As in the other cases, we have the references at the end of the presentation that you can look into. Janelle, I don't know if maybe we have some questions until now before we move on to the other two cases.
Yes. Thank you, Gustavo. Morning, everyone. Questions from Mr. Corbin. He asked, in addition to the reasons provided for reuse, were there any other incentives or disincentives from the government to do reuse?
In the cases I have presented, they were not specifically government incentives, no? But the incentives is directly to the utilities for saving money. In the case of Managua, for example, the farmers go to the plant and they pick up the sludge themselves and take it to their farms. If they don't do that, then it's the utility who has to carry this treated sludge somewhere to the landfill or to dispose of it, right? And disposing of sludge also costs money, right? So if you don't have anybody to pick up the sludge and take it somewhere, then you have to do that with a consequent cost, right? This is different from all the other cases. In the case of Brazil, for example, the incentive is that you are actually selling the treated effluent, right? And you're getting paid for it. So in these cases, in the cases we have shown, the incentive is to reduce the operation of the costs of the plant.
Okay, He also asked, some farmers in the Caribbean are very reluctant to use sewage sludge as a fertilizer. Was there any public education and awareness programs to address any safety or human health concerns?
Yes, in all these cases, there is always very important communication campaigns on this. And usually what you do is that you have to demonstrate that the reuse is safe. You have to demonstrate that there's no risk, right? In order for farmers to adopt the practices. Now, what we also have to take into account is that in many places, the reuse takes place one way or another. So it takes place by default, sometimes even without treating the water, right? So yes, we do have farmers that are reluctant to use sludge, but on the other hand, there's thousands or millions of farmers that are using wastewater with no treatment or sludge without any treatment in other places, right? So the idea is to improve that existing situation into a safer, more regulated situation, right? In the case of Chile, the sludge is goes through very high temperatures and is totally sanitized, right? In this case, maybe the sludge will have some specific restriction, right? But what you do is you classify your sludge, and you can have according to different standards. For example, there's these standards from EPA in which you can have Class A or Class B sludge. So Class A, you can reuse that sludge with no restriction, and you base that on analysis you perform on the sludge. And on a different classification, you will need to use that sludge only as a soil improvement, for example, for forestry or for fodder or for maize, but not for lettuces and tomato and so on. So it depends which opportunity you have, what kind of market you want to serve, and you design your treatment plant and the reuse activity based on those opportunities and needs. Now, another very important fact about treated wastewater and specifically about treated sludge is the initial quality you start with. If, for example, if you have a large facility that collects wastewater from a large area of the city, and in that area of the city you will have not only households, but also industrial activities, hospitals, tanneries, for example, you may end up with other chemicals into your wastewater stream and also into the sludge. For example, you may end up with heavy metals. If you end up with heavy metals in the sludge, basically that sludge is regarded as useless, because to remove those heavy metals from the sludge would be very expensive and it wouldn't be worth it. So it's that's a very important benefit of decentralizing. When you distribute your system and you decentralize the treatment, then you will have treatment plants for industrial areas, and you will have other treatment facilities specifically for domestic areas in which you will have a much better quality water and sludge, and you will not have problems with heavy metals and specific chemicals.
Thank you. Mr. Martin has mentioned that he have seen lamella type settlers used in secondary settling, but do they have a tendency for the plates to block and clog when used in primary treatment?
They have different separation. They are much coarser, no? And they are usually installed in the upper part of the settler. So in the bottom of the settler, you have like a regular settling tank, and the more clarified water on top goes through the lamella settler. But the separation is not as small as the secondary settler. This is a coarser filter, so it doesn't clog.
Okay. Our participant, I'm sorry, I'm not able to pronounce his name and I really don't want to butcher it. He has asked, was health monitoring for the farmers included in the reuse program?
But it depends on the place. I'm not sure about these cases I've presented. In the next two cases I will present, the farmers are part of the project, part of the operation, and they were involved from the beginning in the projects. So yeah, it depends on the case.
Okay.
It is desirable, of course, that farmers are involved from the beginning because they can, in that case, they can be part of the business model, for example, to ensure the sustainability of the treatment operations.
Our participant from CITG asked, what contributed to the reduction of tariff at Aquapolo since they are using reverse osmosis?
Right. Well, the comparison is as compared to drinking water. In the most expensive part of drinking water in Brazil is the very long distances they have to pump drinking water, and also treat the water, of course. But drinking water is very comes from very far away, and that's why it's expensive. But in this case, this treatment plant was closer to this Aquapolo area, or to the petrochemical pole. So the transport of water was the distance was much shorter, and that's why the water was much cheaper.
Thank you. Mr. Headley asked, are there any issues with pharmaceuticals in the sludge? And if so, does it affect the use of the sludge?
Those are the very new issues that people are analyzing. There are many pharmaceuticals going into the wastewater, and especially in Europe, they are paying a lot of attention into this. These are called the new contaminants, the new pollution agents. Very hard to get rid of the pharmaceuticals. One of the methodologies they are exploring, and it's being used currently, is the constructed wetlands that we will see in the next two cases. A very basic technology, but when you have constructed wetlands with plants, it's been demonstrated that you can lower the concentrations of many pharmaceuticals. Yeah. So yeah, pharmaceuticals are present in wastewater. Their concentrations differs a lot from one place to another, but it's a field that is being currently investigated. There's not much information about that.
Thank you. Regarding sludge or gray water, can they be aerated to encourage helpful bacteria for use as probiotics, as fertilizers, or relevant products?
Well, gray water has very low levels of organic load, right? So you can get sludge out of gray water, but it won't become a fertilizer. That sludge, maybe it can help improve the conditions of the soil. It can give a structure to the soil, but it's not regarded as fertilizer because it doesn't have many nutrients in it. It can be aerated. Gray water is usually aerated, so it doesn't produce odors, right? So it's easier to treat gray water than to treat black water, because black water has higher concentration of organic load, so you will have to aerate it more, right? Now, gray water is easier to treat because it's more diluted. So gray water is better to use for irrigation, and you won't get much sludge out of it.
Thank you. Mr. Martin has asked, for the case in Brazil, there were two different tertiary treatment streams, I think UF and RO, used for the industrial reuse of the treatment effluent. Do you know what the different uses were for the two different treatment streams?
No, tell you the truth, I don't know the difference. I know there's many companies those two effluents go to, right? So probably many different processes. I assume the process that goes through reverse osmosis is because the industrial process is more delicate, right? So it needed a higher quality effluent that didn't need minerals in it, and that's why they're running this through reverse osmosis. Just different industry, but I'm not sure which industry this is.
A participant from CITG is asking if the Chile and Nicaragua systems were built with existing sewer systems.
Yes, in both cases, the sewer systems existed. They were conventional centralized sewer systems. And in the case of Chile, they were discharged into the river. And in the case of Managua, to the lake. And in both cases, they were polluting the water bodies.
Thank you, Gustavo. There are no further questions.
Okay, let's move to the next two cases. The next one is Lake Pescaro in Mexico. Very interesting case. This is in the state of Michoacán. The Lake Pescaro sits in a water basin. All that region is a touristic place. It involves 4 municipalities, and in all 4 municipalities, they add up to about 120,000 people. These 4 national organizations got together in 2003 in order to start a program for the protection of Lake Pescaro. Rio Aronte Foundation, the National Water Commission, the National Forestry Commission, and the IMTA, which is the Mexican Institute of Water Technologies. So they all got together and they funded this project for treating wastewater for these 4 municipalities around the Lake Pescaro. In this case, they have used very low-cost technologies, and they have built 6 municipal treatment plants. The plants go from a capacity of 43 cubic meters per day to 432 cubic meters per day. So these are basically small wastewater treatment plants. In this case, the reuse is direct for agricultural irrigation. The water that is discharged to the lake is also used for fish, and they also have pools for fish farming. And finally, for macrophyte production that people that live around the area use for making things, for ornaments and that kind of thing, for handicrafts. Yes. We will see the treatment train here in pictures. First, we have the bar screens at the end, at the inlet of the plant in a grid chamber. Then we have stabilization ponds, and after the stabilization ponds, we have the constructed wetlands. So in this case, the primary treatment is a stabilization pond, and the secondary treatment will be done through constructed wetlands. A constructed wetland, as we have seen in previous sessions, is basically a pool full of pebbles, in this case, gravel. You have a polyethylene liner in the bottom, and you can have 2 types of constructed wetlands. A vertical flow wetlands, in which case you have pipes on top of the wetland, and then you trickle the water through the wetland in a vertical flow. On the last picture on the right, we have the horizontal flow wetland. In this case, the water goes into one side of the wetland and exits on the other side of the wetland. The difference is that the vertical flow wetland is more aerobic, and the horizontal flow is more anaerobic. Another difference is that for the vertical flow wetland, you usually need some pump to pump the water to the top of the wetland. So it also requires a little bit more of O&M operations. You can achieve very high efficiencies in this type of treatment plants. Here we're comparing some of the parameters from 2 of the 6 municipal plants, in this case Santa Fe de Laguna and Cucuchucho. The COD reduction goes from 91 to 93% in one case. In BOD reduction, 97% in the case of Santa Fe de la Laguna. In the other case, from 94 to 98% reduction. Also, from 93 to 97% reduction of total suspended solids. And these treatment plants are less efficient at removing nutrients, right? So they are very efficient at removing organic loads and suspended solids, but they are less efficient at removing nitrogen and phosphorus. But in this case, we don't really need to remove all the phosphorus or nitrogen because we're doing direct reuse. So the effluent of the plant goes directly to the land to irrigate crops. Some of the challenges they have faced between 2013 and 2016, they had some operation and maintenance problems, and some rehabilitation program was put in place to rehabilitate the wetlands that were getting clogged. After this process, operation and maintenance manuals were developed and the operators were trained. We see this type of challenges and problems in many plants, especially on smaller, more decentralized plants that don't have a permanent staff, or maybe they don't have engineers, or they don't have all the resources in order to solve problems. So that's why it's very important to implement management model that is according to the needs and the technical competencies and needed for every system. So in very large centralized systems, we might have all the technical staff working on site at the plant, right? But in this smaller, more distributed system, we have to link the system to an institution or to staff that will be capable of supervising, operating, maintaining the system, as we have seen on previous sessions when we were talking on the management and the business models in order to ensure the sustainability of the systems. And finally, we will look at experience in Bolivia, which I have participated from directly. In this case, we're talking about an area away from Cochabamba city, in which there are several small towns between 5,000 and 30,000 people. They were polluting the basin in this area, polluting several rivers and a reservoir of water. There is a lot of existing agricultural activity in the area. The area is very dry. We get less than 400 millimeters of rain a year. And the main water source for irrigation used to be rain and deep boreholes. So farmers tend to drill deep boreholes from maybe they range from 100 meters to 120 meters deep, and they have to pump this water for irrigation. Since they have to pump the water from these deep boreholes, then the cost of water becomes expensive, but that's what they have to rely on. Here in this satellite image, we see 3 urban centers. One is called Punata with 30,000 people. The second one in the bottom is Clisa with 10,000 people, and the one on the left is Tolata with 5,000 people. And you can see the agricultural activity, this more green area around these urban centers. So we developed a project with the cooperation of the Swedish Embassy in Bolivia, SIDA, in partnership with the municipalities. The implementing agency was Aguatuya Foundation, and an NGO I've been working for a long time. The Aguatuya Foundation did all the designs, all the engineering, the implementation of these plants, and also manages and operates these plants under a contract with the municipalities. From the beginning, all these treatment plants have a reuse approach for the sludge and also for the treated effluent. Here we can look at the capacity of the treatment plants. In the case of CLISA, is around 570 cubic meters per day. It's been implemented in 8,000 square meters and an investment cost of $500,000 US. Tolata is a smaller plant, implemented in an area of 3,000 square meters with a capacity of 326 cubic meters per day. And the third one is the largest of these three, with a total investment of $1.2 million US, 50,000 square meters and a capacity of 2,500 cubic meters per day. So we have an interesting range of small to medium treatment facilities. This is the smaller one. You can see the anaerobic reactors in the back. This is not a classic UASB reactor. This is a horizontal reactor. It's more like a baffle reactor in which water goes into the first chamber, then moves to the second chamber, then to the third chamber. And as water goes under a primary treatment. And after that, we have an unplanted gravel biofilter. So this is similar to a constructed wetland, but we don't have plants, so we call it an unplanted gravel biofilter. We are combining here vertical flow and horizontal flow, as we will see later on in another diagram. In this picture, we see also anaerobic reactors. This one is for 10,000 people. And in the background, you see all the reuse activity in irrigation of maize and alfalfa. So in this case, this plant does not have a disinfection step. So we have restricted reuse for irrigation. So basically, the treated effluent is reused for irrigation of fodder, maize, alfalfa, but not for lettuces, tomatoes, and other types of crops. So that's the type of combination you can have also. Either you treat the water to a higher degree, to a higher level in order to have unrestricted irrigation, or you treat the water to a lesser degree, but you have some restrictions for irrigation. So this is the multiple phase approach of World Health Organization, multiple barrier approach to irrigation. In this case, you can see all the land being prepared for irrigation with the treated effluent. Here we're looking at solar drying of sludge. So these anaerobic reactors also generate sludge, but in this case, we have little rain, only some months of the year, maybe 2 or 3 months of the year, and the rest of the year is very dry and windy, so you can just put the sludge to dry in the air. Here we can see the plant in the center of the image, and on the right and also on the left, we can see the area under the influence of the irrigation. We have about 20 hectares on top and also 20 or 21 hectares in the bottom part. So all that area marked in green can be irrigated with the treated water from this small town of 10,000 people. Here you can see the farmers moving a polyethylene pipe that pumps water from the effluent of the pump towards their parcels. And now we will take a look at the treatment train here. First, we pump the water into the plant. We have automatic revolving screen for fine screening here, fat separation, the horizontal anaerobic reactor, similar to a baffle reactor that we saw on the picture. Then we have the gravel filter, first the horizontal filter, then the vertical flow filter. Then optionally, we have a chlorination tank that we can use in case we want to reuse the effluent into some unrestricted crop. And as similar to the other case, we have efficiencies of around 90% and higher for BOD, for COD, and for suspended solids, and around 40% for the reduction of nitrogen and phosphorus. What I want to highlight in this case is the approach to a circular economy model. First, before we did this project, we had a linear approach to wastewater treatment. We have deep boreholes for drinking water, so fresh water from the boreholes was pumped into the city, is still pumped into the city. The water is used in the city, it turns into wastewater, and it was discharged untreated into the river. That was the previous situation. And people, in parallel, farmers around the city, around the small town, would grow their crops. They would irrigate the crops using water coming from the boreholes, pumping that water. Also, they would use water from rains. And in some cases, they would also use the water from the river, which was very polluted, so untreated water being used for irrigation, especially when they didn't have access to a deep borehole. And we also show here in the bottom the fertilizers coming into the cropland, and then the crops going into the city for food for the citizens. So this is what we have under a linear approach, in which we get fresh water from somewhere, we use it, and we dispose it to the river untreated. And there's not much connection between the farmers and the sewer system. So what we have changed with the project is we have built wastewater treatment plant. So the wastewater coming from the city will be treated, and then once it's treated, it will be discharged into the river. First, we're creating a reuse approach here, because the treated water goes into the river, and the river will appropriately recharge the aquifers with water that is not polluted, right? So we have a virtuous cycle here instead of the vicious cycle we had in the past. But more importantly, here, the treated effluent of the plant still has nutrients and can be used for irrigation of the crops. So in the past, the farmers had to rely on more expensive water coming from the boreholes, or they have to rely only on rain, which is very scarce and is not reliable, because the farmers are usually waiting for the rainy season to come in order to plow the fields. And if the rainy season comes late, then they miss the chance. So from the wastewater, they have a very, very reliable flow all year round that they can use. And the actual impact and benefit that they have obtained from this system is that in the past, the farmers here would have only one crop a year, and now they have 2 crops a year, two times. So they have basically doubled their production, only because they can rely on the effluent of the treatment plant, on the treated effluent. They are still also using the rain, and that's a very good combination, because as we have seen in previous sessions, the treated wastewater might have higher levels of salinity, so it's a very good idea to combine with other irrigation schemes. But the crops go to the city, and the nutrients go again to the treatment plant and back to the crops, and so we have the circular approach here. And we're closing the water loop, and we're also closing the nutrient loop here. And we're putting less pressure on the aquifers because we're substituting the water from the underground resources by water coming from the sewer, and we also substituting imports of fertilizers. So then we can see in this table the net effect of reducing the discharge of BOD in the river. Only talking about these three plants, for the population we mentioned, we reduced the BOD being discharged into the river from 240 tons a year to only 6. That's a 97% reduction. Suspended solids from 167 tons per year to 6. And the nutrients also have been reduced. The nutrient discharge into the river has also been reduced a lot, from 37 tons to 14 tons, so a 62% reduction. From 5 tons a year to 2 tons a year for phosphorus, 57% reduction. And we're also reducing, as I mentioned, the pressure on underground resources and fertilizers. So this is the amount of fertilizer we were able to substitute, and the amount of water, of fresh water, we are able to substitute every year. So 300,000 cubic meters per year of underground water extraction, and 12 tons of fertilizers that we don't need to import. I think for the conclusions, for all the cases in general, we have learned that the level of treatment depends on the type of reuse intended. So we have to start from the back. Identify our opportunities for reuse, and then design the appropriate treatment plants. Depending on the local needs, we can opt for very large centralized systems or smaller or decentralized systems. So it's not that one plant is better than the other. We need larger plants for large, dense areas of certain cities, but we also need very small, decentralized, smaller scale plants for peri-urban areas, rural areas, for institutions, for places that are not connected to a centralized scheme. Only a combination of these distinct and complementary systems can solve the wastewater problem. Reuse in agricultural irrigation offers a triple benefit. First, water resource conservation, nutrient recovery, and eutrophication prevention. Finally, the reuse generates opportunities for circular economy, as we have seen, because we're turning waste into resources. Okay, do we have any questions, Janelle?
Yes,
because at least we have communication with our guest, right?
Okay. We have a question from Rachel. She noted that the systems look rather vast for the Caribbean, which has limited flat space due to our topography. She asked, is there a reason for volume of waste to minimum treatment area? For example, for the wetlands, secondary, tertiary treatments. Have you seen treatment plants on undulating land? Thank you.
Yes, that's a very interesting question, very important question. There's a trade-off. When you use a passive technology, such as stabilization ponds, right? Those are very low-cost technologies, but you will need larger areas, right? So the treatment technology that needs the most area is stabilization ponds. If you replace stabilization ponds by constructed wetlands, you need less area, right? But if that area is still too large, then you have to go to more compact technologies. More compact technologies are available, but in that case, the trade-off is that you will need more energy input. Right? So you can have very, very compact plants, but in that case, you will need more energy. In undulating land, yes. If the city is an undulating in an undulated terrain, then maybe it's a good idea to decentralize and have different plants in different places, right? Now, if you're talking about the site of the treatment plant, you want to implement one plant in an undulating place, then you can also do that, and because you can have that to your advantage, you can have, for example, one vertical constructed wetland higher, and then the next step below. So through gravity, you can move water from one step to the next. So yeah, you can have very compact plants, but the trade-off is that you will need more energy. For hotels, for example, what we're using for hotels are plants based on submerged aerated filters. And on next session next week, we will look at some of those more compact plants for small communities, for neighborhoods, for hotels, that kind of thing. More decentralized, more compact.
Thanks. So I just noticed that Risha mentioned that the question was focused on agriculture, livestock, crops, aquaculture as well. So yeah.
Yes, that's correct. Aquaculture is a reuse that a very interesting reuse opportunity also.
Okay. David has asked, are slopes good for flows in constructed wetlands, large savings in energy due to gravity, with no pumping?
Yes, the slope is good. You need a minimum slope, but of course, whenever you have a slope, you can move the water by gravity and then save money. Of course, yes. Many treatment plants work only by gravity. They usually stabilization ponds work fully on gravity. You just need minimum difference of level to maybe 2% difference in order to move water from one pool to the next.
Mr. Harnden is asking, do you have an example of terraced series of ponds and wetlands on sloped land?
Yes. What you do is you build like terraces, right? You build like terraces. The pond itself cannot be on the slope land, right? You build like terraces, so you level one area, and then you have the next pond at a lower level, right? So you have to flatten at different levels, like terraces, in order to use that difference in levels to your advantage. But the pond itself has to be, of course, in a flat area.
Ron Martin, before designing and constructing the wastewater treatment system, having beneficial uses, is there a stakeholder engagement meeting? If so, what are some of the stakeholders who are involved? For example, water and sewage utility, farmers, industries, etc.
Right. It's very good to involve all the stakeholders from the beginning. In the case of the last case I presented, for example, the municipality had no place in which to build a treatment plant, and nobody wanted a treatment plant close to their homes, right? But once we demonstrated the farmers of the advantages of the treated effluent, and the farmers saw this benefit of having access to the treatment effluent and a very stable water source during the entire year, then they decided, the farmers themselves, they would give the land to the municipality for the construction of the plant. So In one of the cases, they turn about 8,000 square meters of land, of community land of the farmers, towards the municipality in exchange of the of having access to the treated effluent, right? So those were the negotiations between the stakeholders, in this case between the municipality and the municipal utility and the farmers that needed that water, and the municipality needed the land for building the treatment plant. So you can create these synergies when you approach the stakeholders and get them on board from the beginning of the project.
Yeah.
Okay, so
you.
now we have some. Thank you, Janelle. Thank you a lot. We have some good news and some very interesting initiative, which will be presented to us by Selen Trip. So that's today. He's a representative of Borda, Breven Overseas. They are based in Germany, but also in Central America and in Mexico several years ago. And she will present her institution and herself. Please, Selen, if you can tell us a little bit about Borda and also about this very interesting initiative.
Thank you, Gustavo. Well, Borda is an organization that works in the development and implementation of integrated water and sanitation solutions all over the world. I'm working specifically in Mexico. I'm a project coordinator here, and I would like to use this time to present you one of the newest projects that we're working on together with GIZ. So, as you already know, through all these courses with Crew Plus Academy and with Gustavo, the sustainable treatment of wastewater and fecal sludge is a crucial component for the access to safe sanitation. However, the discharge of untreated waste or partially treated waste is one of the greatest contributors to or threats to the aquatic ecosystems in the Caribbean region, where in this region the current sanitation systems are insufficient or inefficient, becoming one of the largest contributors to public health deterioration, the reduction of freshwater quality, and the pollution of the marine environment. And this also has some other impacts in other sectors, such as tourism, which is one of the more important economic activities in the Caribbean. Facing these challenges, there are different initiatives which encourage the development and the implementation of the sustainable sanitation solutions in the Caribbean countries. In the existing literature and knowledge of the sector, as well as you have, Gustavo already pointed out, during these courses, the sanitation systems are a set of technologies and also operation schemes that need to be context specific in order to achieve their targets. And so, however, we have identified that there are very limited publications or information available contextualized to the wider Caribbean region. There is a lack of regionalized literature with information that is adequate and context-specific to the geographic, climatic, hydrological, and even socioeconomic and cultural characteristics of this region. Well, in this context is that Borda, in alliance with GIZ, has taken up the mission to develop a compendium of sanitation systems and technologies specifically for the Caribbean region. With this, we are aiming to contribute to the generation of specialized literature and contributing to increase the local capacities and promote the establishment of sustainable and innovative approaches towards the wastewater treatment in the Caribbean. In this sense, we are in the quest of guiding on the selection of appropriate wastewater treatment solutions through regionalized, contextualized, and application-oriented knowledge. The objective is to develop a compendium of systems and technologies that do adjust to the needs of the Caribbean region. This compendium will take as a reference some of the existing compendiums, such as the one published by Iwag and Susana, and which cover you can see on your screen. But in this case, the compendium will be specifically for this region, and it will also regain the experiences of previous projects for the implementation of nature-based solutions in the region. I'm sorry, there's a train coming. sorry about the noise. I hope it goes. So we are trying to generate this compendium that will regain the experiences of previous projects in the region for the implementation of nature-based sanitation solutions in the Caribbean. So for building up this compendium, we are looking for professional experts, suitable organizations, academic and research institutions from the Caribbean countries that are linked or engaged with sanitation systems development or the service provision. And this is why I'm here to invite you and to engage your participation in the development of this compendium and contribute with your knowledge and your expertise. Okay, and how is it that you can contribute to this compendium? I'm sorry again about the noise. How you can contribute to this compendium? I am very happy to invite you to a kickoff workshop that we'll have next week to discuss the background and the objectives of this specific project, as well as the details on how you can contribute to the development of the compendium. This workshop will happen online next Friday, 1st of October from 9 to 10:30, same time as this course. And you will find the link right here. I'm just sending it on the chat window. You can get registered and we'll send you the link to the workshop. Thank you very much for your time. Sorry again about the noise. And I'm really looking forward to seeing you next week.
Thank you, Selene. Great to have you here. Everyone, please do register for this important kickoff workshop. Don't miss the train. The link is on the chat box. Thank you again. Well, with that, we have finished the presentation, today's session. You will be able to find all the session materials at the Web Academy website. The link is on the screen. And Janelle will also paste the link for the materials in the chat box. And Selene has pasted the link for the kickoff meeting next week for the compendium initiative, so you can access to. Thanks everyone for your presence today, your attention and your questions. It's been a pleasure to facilitate this session. See you next week on the last session on decentralized wastewater treatment and reuse. Over to you, Chris.
Thank you so much, Gustavo. So while participants are completing the final survey, I just also want to thank Gustavo again for your excellent facilitation. I want to thank Celine for the presentation, and particularly to thank all of the participants for being so engaged. Your questions, very, very relevant. Many of you, of course, from the smaller East Caribbean English-speaking islands. And it was really good to see how you were able to take some of the lessons learned, even from our larger Latin American neighbors, to see how it could apply within a small island context and within a Caribbean context. In that regard, we really do look forward to you joining us next week, Thursday, same time, same place, for the final webinar that will in fact focus on smaller, decentralized, community-based, and rural type of solutions. So what we saw today was targeting perhaps some larger industry, larger cities. Next week, we're getting even smaller, and we look forward to all of you registering. It's going to be the final webinar in this series.